Welcome to Cosmic Sedation, your peaceful retreat into the night. Tonight's topic, the hidden realities of life on Mars. Let's dive deep into what it truly means to call the red planet home. Don't forget to subscribe and like if you're enjoying this journey. Where are you listening from tonight? What time do you usually drift off? As we begin, let the calm wash over you. The red dust that blankets Mars is not a passive residue of time, but rather the ongoing product of cosmic violence, each grain sculpted from micrometeorite impacts over billions of years. On this distant world, silence is absolute. There are no molecules to carry sound through its thin atmosphere, yet it is bombarded incessantly by particles from space. One such impact can release energy equivalent to a small nuclear explosion on Earth, though the vast distances between Mars and potential sources make these collisions rare enough that they accumulate over eons rather than years. Each collision fractures or melts bits of the Martian surface, adding to the ever-growing layer of regolith, a term scientists use for this loose soil. The process by which micrometeorites contribute to regolith formation is not uniform across Mars. In regions where ancient volcanoes once spewed lava and ash, the composition of the dust differs from that in other areas. The presence of volcanic materials means these zones have a higher concentration of silicate minerals, which can affect how effectively the regolith traps heat or reflects sunlight. This variation highlights the diverse geological history of Mars, each region telling its own story through the particles it hosts. Consider now, if you will, the sheer volume of material involved in this process. The total mass of micrometeorites hitting Mars each year amounts to about 10 tons, an amount that might seem paltry compared to Earth's annual meteorite influx of hundreds of times more. Yet over 4.5 billion years, these impacts have built up a layer of regolith averaging several meters in thickness across much of the planet. It is as if every grain of sand on Mars bears witness to countless cosmic bullet wounds, each one marking an infinitesimal fraction of the universe's violent past. And while such a process might seem insignificant against the backdrop of time itself, it plays a crucial role in shaping the Martian surface into what we see today. The regolith formation is not just about dust. It also involves ice and salts, substances that influence the planet's climate and potential habitability. When micrometeorites strike Mars, they can vaporize water ice trapped within the soil, creating localized atmospheric disturbances. These mini-atmospheres are temporary, lasting mere seconds before dispersing into the thin Martian air. The resulting clouds of water vapor contribute to a cycle that subtly influences global weather patterns and dust storms. This process underscores how even minor cosmic events can have far-reaching effects on planetary systems. Imagine now the journey of a single particle from space to Mars. As it hurtles towards the planet at speeds reaching tens of kilometers per second, it encounters the thin Martian atmosphere. The friction generated during its entry causes the micrometeorite's surface to melt and evaporate, leaving behind a trail of ionized gas in its wake, an effect that would be spectacular if observed from Earth. Once past this initial heat barrier, the particle strikes the surface, wear upon it either shatters into smaller fragments or forms a small crater. The temperature at the point of impact can exceed 230 degrees Celsius, hotter than molten lava on Earth, and yet within seconds it cools to Mars' average temperature of degrees Celsius. This extreme thermal cycling is part of what makes Martian regolith so unique, and its composition such a valuable study for understanding planetary formation. While the micrometeorite impacts are responsible for much of the dust on Mars today, they also played a role in shaping the planet long before life emerged on Earth. Billions of years ago, when the solar system was still young and chaotic, Mars endured an even higher rate of bombardment due to the early stages of asteroid belt formation and more frequent close encounters with other celestial bodies. This period is known as the Late Heavy Bombardment, during which Mars likely had a much thicker atmosphere and possibly liquid water on its surface. The craters left behind from this era serve not only as evidence of past events, but also as time capsules containing clues about Martian history. Some of these ancient impacts may have even delivered organic molecules to early Mars, potentially seeding the conditions necessary for life. The paradoxical warmth generated by Martian dust storms may seem counterintuitive at first glance. While Mars averages degrees Celsius, these colossal storms can heat the atmosphere more than direct sunlight does on Earth. This effect is particularly pronounced during global storms that envelope the entire planet for months. During a typical Martian day, temperatures vary dramatically due to solar radiation and atmospheric conditions. However, it's the swirling clouds of fine red particles that create an unexpected phenomenon. They absorb solar radiation and re-emit it as infrared light, warming the surrounding air. This process is akin to how dark pavement warms more than adjacent snow during sunny days on Earth. On Mars, this effect can raise local temperatures by up to 30 degrees Celsius. Imagine standing inside a Martian dust storm. The fierce winds might buffet your spacesuit, but you would feel an unusual warmth that defies the cold environment. These particles are finer than those found in Earth's deserts, making them perfect for trapping and re-emitting infrared radiation. With wind speeds reaching up to 160 kilometers per hour, these storms can cover vast areas across Mars' surface, stirring dust clouds over thousands of kilometers. What causes this paradox? The thin Martian atmosphere, composed mostly of carbon dioxide, amplifies the effects of trapped solar radiation. This process is crucial for understanding how energy flows on Mars. For context, the average distance between Mars and Earth is about 225 million kilometers, so far that radio signals take over 20 minutes to travel each way. The storms are so powerful that they can cover an area larger than North America in a matter of days. While these storms create warmth, they also pose significant challenges for human exploration. The iron oxide-rich dust can damage equipment, clog systems, and even seep into spacesuits during extravehicular activities. Yet, this dust holds another surprising quality. It could be a key resource for future colonists. Its unique composition allows for potential uses in creating breathable oxygen or even cement-like materials. The scale of these storms is immense, lasting months with winds that can shift across the planet's surface over vast distances. In human terms, imagine such a storm persisting continuously for years. It would be akin to experiencing relentless weather systems without breaks, reshaping landscapes over time. Each grain of dust is a remnant of ancient asteroid impacts, telling stories older than any mountain on Earth. These storms also play a crucial role in redistributing nutrients across the Martian surface, much like how wind patterns spread seeds on Earth. They are both a hazard and an opportunity for future settlers, transforming Mars' environment in ways that could one day support life beyond its initial cold embrace. The paradoxical warmth generated by Martian dust storms may seem counterintuitive at first glance. While Mars averages degrees Celsius, these colossal storms can heat the atmosphere more than direct sunlight does on Earth. This effect is particularly pronounced during global storms that envelope the entire planet for months. During a typical Martian day, temperatures vary dramatically due to solar radiation and atmospheric conditions. However, it's the swirling clouds of fine red particles that create an unexpected phenomenon. They absorb solar radiation and re-emit it as infrared light, warming the surrounding air. This process is akin to how dark pavement warms more than adjacent snow during sunny days on Earth. On Mars, this effect can raise local temperatures by up to 30 degrees Celsius. Imagine standing inside a Martian dust storm. The fierce winds might buffet your spacesuit, but you would feel an unusual warmth that defies the cold environment. These particles are finer than those found in Earth's deserts, making them perfect for trapping and re-emitting infrared radiation. With wind speeds reaching up to 160 kilometers per hour, these storms can cover vast areas across Mars' surface, stirring dust clouds over thousands of kilometers. What causes this paradox? The thin Martian atmosphere, composed mostly of carbon dioxide, amplifies the effects of trapped solar radiation. This process is crucial for understanding how energy flows on Mars. For context, the average distance between Mars and Earth is about 225 million kilometers, so far that radio signals take over 20 minutes to travel each way. The storms are so powerful that they can cover an area larger than North America in a matter of days. While these storms create warmth, they also pose significant challenges for human exploration. The iron oxide-rich dust can damage equipment, clog systems, and even seep into spacesuits during extravehicular activities. Yet, this dust holds another surprising quality. It could be a key resource for future colonists. Its unique composition allows for potential uses in creating breathable oxygen or even cement-like materials. The scale of these storms is immense, lasting months with winds that can shift across the planet's surface over vast distances. In human terms, imagine such a storm persisting continuously for years. It would be akin to experiencing relentless weather systems without breaks, reshaping landscapes over time. Each grain of dust is a remnant of ancient asteroid impacts, telling stories older than any mountain on Earth. These storms also play a crucial role in redistributing nutrients across the Martian surface, much like how wind patterns spread seeds on Earth. They are both a hazard and an opportunity for future settlers, transforming Mars' environment in ways that could one day support life beyond its initial cold embrace. Im start, Musciat Reif Weiber Jail Weiber Lesbisch Pornost. Water behaves quite differently on Mars than it does on Earth, due to the planet's thin atmosphere and low pressure. At first glance, this might seem like a simple matter of temperature. After all, Mars averages degrees Celsius. Yet, what truly sets Martian water apart is its inability to exist as liquid for long periods under these conditions. On Mars, if you were to pour out a glass of water, it would instantly vaporize or sublimate into gas without passing through the familiar liquid phase we know on Earth. This process occurs because the atmospheric pressure on Mars is only about 0.6% of Earth's sea level pressure. To put this in perspective, the boiling point of water at Martian surface pressures is around -73 degrees Celsius, far below the temperature needed for liquid water to form. On Mars, the very act of melting ice becomes a complex and fleeting event. Ice placed on Mars would first sublimate directly into vapor without ever forming droplets. This behavior contrasts sharply with earthly expectations, where ice melts at 0 degrees Celsius under standard atmospheric pressure. The low-pressure conditions on Mars defy our intuitive understanding of water's phases, transforming what we consider a straightforward process into something unpredictable and rare. On Earth, melting is an easily observable transition, but on Mars, it becomes a brief anomaly, quickly erased by sublimation. Imagine standing at the edge of one of Mars' polar ice caps. You might expect to see snow and ice forming lakes or rivers as they do on our planet, but that would be far from accurate. Instead, you'd find vast expanses covered in frost or dry ice, with only a trace amount of water vapor suspended above them. The sublimation process here operates on such a rapid scale that it is almost invisible to the naked eye. Yet, this process has profound implications for potential human exploration and colonization efforts. To sustain life as we know it, significant engineering solutions will be needed to maintain liquid water in artificial environments under Mars' extreme conditions. The peculiar behavior of water on Mars also affects its potential to support biological processes. In Earth's environment, water is the solvent that allows biochemical reactions necessary for life to occur. On Mars, however, this capacity is greatly diminished due to the rapid vaporization. This creates a paradox. While there may be ice and ancient reservoirs locked beneath the surface, maintaining liquid water at the Martian surface level remains an extraordinary challenge. The idea of melting ice on Earth seems so simple. Yet here, it becomes a complex scientific endeavor requiring precise control of environmental conditions. Further complicating matters is the fact that even if one could manage to create a small pool of liquid water on Mars' surface, its lifespan would be incredibly short. Within moments, any exposed water would vaporize away into the thin Martian atmosphere. This underscores the delicate balance between temperature and pressure needed for stable liquid states to exist. On Earth, we take for granted that liquid water is abundant in our environment, but on Mars, it exists only fleetingly and under highly controlled conditions. Understanding these unique properties of water on Mars provides valuable insights into the planet's potential for supporting life or hosting future human settlements. The challenges posed by sublimation highlight the necessity of advanced technology to manage even basic resources like water in such an extreme environment. As we continue to explore Mars, both through robotic missions and with ambitious plans for human habitation, the peculiarities of its water cycle will remain a critical consideration, shaping how we approach this distant world's future. Imagine stepping off a spacecraft onto Mars, your boots sinking slightly into the red dust. The gravity here is just 38% of Earth's, making every step feel lighter than you might expect. Your body adjusts to this new environment, each movement requiring less effort than on our home planet. However, beneath the sensation of weightlessness lies a subtle challenge. Muscles accustomed to supporting your full mass now have little to do, leading to potential atrophy over time. To illustrate, consider that in reduced gravity, even simple tasks like walking become an exercise in balance and control. Your body must recalibrate its sense of equilibrium, much like learning to ride a bicycle for the first time. This adjustment is not just physical, but also neurological. Your brain relearns how to coordinate muscle movements efficiently. On Earth, the familiar tug of gravity keeps muscles engaged even when at rest, whereas on Mars, this constant pressure is absent, leading to a gradual weakening if proper countermeasures are not taken. As you walk, every step compresses the Martian regolith beneath your feet, sending tiny vibrations through the ground. These disturbances would be imperceptible in Earth's atmosphere, but here they might offer a sense of presence, though sound cannot travel without air molecules. The reduced gravity also affects your perception of speed. What feels like a brisk pace on Mars could translate to an almost leisurely gait elsewhere. This shift can disorient initially, yet it also opens up possibilities for new ways of locomotion that we might not have considered on Earth. For instance, you might find yourself skipping or hopping more frequently than walking due to the ease with which your body moves in this lighter environment. The lower gravity on Mars has another intriguing consequence: the way shadows behave. With less gravitational pull, objects cast longer shadows than they would on Earth. This phenomenon is particularly noticeable near Olympus Mons, where towering cliffs and volcanic slopes stretch out under elongated umbra. These exaggerated shadows hint at the vastness of the landscape and the scale of geological formations that dwarf human experience, reminding us of how small we are compared to the forces that shaped this world. In addition to walking, jumping on Mars would be an entirely different experience. A person could leap higher and cover greater distances than they ever could on Earth due to the reduced gravity. However, the thin Martian atmosphere means there is little resistance against falling back down, leading to a sensation of free fall for longer periods than you might anticipate. This unique combination of lightness in movement and prolonged descent creates an eerie sense of floating, yet with the constant reminder that Mars is far from Earth-like. While exploring, your body undergoes subtle changes due to this reduced gravity. The fluid within your inner ear the organ responsible for balance, adjusts to the new conditions. This adaptation can sometimes result in a form of motion sickness as your brain struggles to interpret conflicting signals. Yet over time, these symptoms subside, and you might find yourself moving with an elegance that is distinctly Martian. Despite the challenges, there's an undeniable charm in this lighter way of being, where each step carries less weight than it does at home. In the heart of Mars' polar regions, a unique phenomenon unfolds as winter tightens its grip on the red planet. Carbon dioxide ice begins to sublimate directly into vapor at temperatures that would chill the coldest places on Earth, reaching down to minus 128 degrees Celsius. This process occurs in an atmosphere so thin it barely clings to Mars' surface, containing just 0.13% oxygen compared to Earth's rich air. The ice here is not merely frozen, but locked in a delicate balance with the planet's tenuous atmosphere, transforming from solid to gas without passing through a liquid phase. This sublimation subtly affects atmospheric pressure and weather patterns across Mars. On Earth, such transitions happen smoothly and slowly, often unnoticed by human observers. Yet on Mars, where the air is so sparse, this cycle becomes a significant factor in shaping the planet's climate. Each gram of CO2 ice that turns into vapor adds to the already meager atmosphere, incrementally altering pressure at the poles. By late spring, the atmospheric pressure can be 15% higher than it is during summer, marking a stark seasonal shift. This transformation is not just about changing weather. It impacts everything from dust storm patterns to wind speeds across the Martian surface. For humans living on Mars, these fluctuations present both challenges and opportunities. Any habitat must be meticulously sealed against the elements or risk depressurization as the air becomes thinner during certain seasons. The sublimation process at Mars' poles is particularly intriguing when compared to Earth's ice cycles. On our planet, glaciers melt into liquid water before evaporating. On Mars, this phase is skipped entirely due to the thin atmosphere and low pressure. This direct transition from solid to gas, known as sublimation, contrasts sharply with Earth's rapid melting glaciers, highlighting the unique nature of processes on Mars. The ice sublimation is not just a passive event. It actively participates in shaping the planet's environment over time, influencing everything from weather patterns to dust storms that can envelop the entire globe. The thin Martian atmosphere contains only 0.13% oxygen, making it inhospitable for humans without extensive life support systems. Yet, this same atmosphere plays a crucial role in regulating temperature and pressure on Mars. The CO2 ice at the poles sublimates directly into vapor, significantly altering atmospheric conditions as winter transitions to spring. This process is not just about weather. It impacts everything from dust storm patterns to wind speeds across the Martian surface. Moreover, the sublimation process has implications for future missions aiming to understand or even alter Mars' environment. The CO2 released during these cycles could one day be harnessed for terraforming efforts, offering a glimpse into how Mars might have supported life billions of years ago. This delicate balance of ice and gas at the Martian poles is not only crucial for understanding current conditions, but also provides insights into the planet's distant past and potential future, making it a vital area of study for astrobiologists and planetary scientists alike. Understanding this process also opens doors for future exploration. The potential to harness CO2 ice for resources or even climate modification projects is tantalizing. Imagine using the sublimated gas to create breathable atmospheres in sealed habitats, or even terraforming efforts aimed at making Mars more Earth-like over time. While such endeavors are far from immediate, they underscore the intricate web of possibilities that Martian science offers. Each gram of CO2 ice that sublimates today is a step towards unraveling the secrets of this enigmatic world, a distant cousin to our own. The seasonal cycle of sublimation at Mars' poles is a testament to the planet's unique environmental dynamics. It demonstrates how, even in conditions far removed from Earth, life-supporting processes can emerge and evolve. This delicate balance between solid ice and gaseous CO2 not only shapes Mars' current climate, but also holds clues about its distant past. By studying this process, we gain insights into the potential for life elsewhere in our solar system and beyond. As night falls on Mars, the sublimation of CO2 ice continues at the poles, a silent reminder of the planet's ancient history and ongoing transformation. This cycle is not just about weather or climate. It's also a window into the vast cosmic timescales that govern planetary evolution. The pressure changes caused by this process are so subtle yet profound. They could influence future human endeavors on Mars, from habitat design to potential terraforming projects. Each year, as the ice sublimates and reforms, it paints a picture of a world in constant flux, shaped by forces both ancient and ongoing. The temperature difference between the polar regions and the rest of Mars is stark, with the poles experiencing temperatures that can drop to -130 degrees Celsius, compared to the equatorial regions, where summer highs reach around 20 degrees Celsius. This extreme cold plays a crucial role in maintaining the CO2 ice cycle, as it keeps the atmosphere thin and prevents any significant retention of heat. The contrast between these frigid areas and the warmer equatorial regions highlights how temperature variations can drive global atmospheric dynamics. These dynamics are not just local phenomena, but have far-reaching effects on Mars' overall climate system. The sublimation process at Mars' poles is also influenced by solar radiation, which varies with the seasons. As the sun's energy increases during spring and summer, more CO2 ice transforms into vapor, contributing to the seasonal pressure changes. This slow but significant transformation contrasts sharply with Earth's rapid melting glaciers, highlighting the unique nature of processes on Mars. The ice sublimation is not just a passive event. It actively participates in shaping the planet's environment over time, influencing everything from weather patterns to dust storms that can envelop the entire globe. In the desolate landscape of Mars, where temperatures plummet to degrees Celsius on average, there exists an invisible threat: ultraviolet radiation. This force, far beyond human perception, shapes every aspect of survival on the red planet. Specialized instruments known as ultraviolet sensors are indispensable tools in this environment. These devices meticulously track wavelengths of light that would otherwise go unnoticed by humans. For instance, ultraviolet sensors on Mars have detected radiation levels reaching up to 20 times stronger than what we experience at sea level on Earth. This intensity is comparable to standing under a high-intensity tanning bed lamp without any protective gear. When astronauts step out of their habitats, these sensors become their silent companions. While the Martian sky might appear serene in its pink or tan hues, beneath this tranquil veneer lies an unrelenting barrage of solar radiation. Ultraviolet rays pose not only skin damage, but also threaten to degrade materials and compromise sensitive electronics critical for survival on Mars. Each sensor acts as a vigilant guardian, ensuring that vital equipment remains operational despite the harsh conditions. Interestingly, these sensors reveal how Martian dust storms play a role in modulating ultraviolet levels. During massive planetary storms, when the atmosphere thickens with suspended particles, some of the radiation is scattered and its intensity temporarily reduced. However, even during these periods of relative calm, ultraviolet radiation does not disappear entirely, constantly reminding inhabitants of Mars's relentless hostility. Beyond their immediate protective function, ultraviolet sensors serve as crucial tools for understanding Martian weather patterns and atmospheric composition. By measuring fluctuations in ultraviolet radiation, scientists can infer the changing nature of dust clouds and how they interact with sunlight over time. This data provides insight into both current conditions and historical climate changes on Mars. It's through this meticulous observation that we piece together the complex history of its atmosphere. Moreover, these sensors offer valuable lessons about Earth's future as well. The way ultraviolet radiation interacts with dust and gases on Mars can inform us about similar processes that might unfold on our planet if environmental conditions shift dramatically over millions of years. As we peer into this alien environment through the invisible eyes of ultraviolet sensors, we gain not only knowledge, but also perspective on both Mars's past and Earth's potential future. The harsh realities faced by inhabitants of Mars are further exemplified when considering the long-term effects of prolonged exposure to such intense radiation. While humans might shield themselves within habitats, plants, and any biological experiments left exposed would face severe challenges. Ultraviolet radiation can alter DNA structures and inhibit growth, making it crucial for researchers to understand these impacts fully. This knowledge is vital not only for current missions, but also for future human endeavors on the planet. Another critical function of ultraviolet sensors is their role in understanding how the Martian surface itself contributes to radiation levels. The red dust covering Mars's terrain, a result of billions of years of cosmic bombardment, can reflect and scatter solar radiation in unexpected ways. These interactions not only affect current radiation levels, but also provide clues about past environmental conditions on the planet. Finally, these sensors reveal that while ultraviolet radiation is an ever-present threat, it also holds potential for future exploration. By understanding its behavior, scientists can develop technologies to harness this energy for power or even use it in innovative ways for human survival. As we continue to probe Mars's secrets through these invisible eyes, the possibilities for discovery and adaptation expand endlessly. In the Martian highlands, ancient rocks bear witness to magnetic fields that once thrummed through the planet like a heartbeat. These anomalies are not just remnants of Mars' distant past. They offer insights into Earth's volcanic history as well. Each rock tells a tale of molten lava cooling in the presence of a strong magnetic field, aligning its minerals with the direction of the ancient Martian dynamo. On Earth, similar patterns have been studied to map out periods when our planet's own magnetic field reversed. These reversals are like timestamps, marking epochs when north became south and back again. Imagine standing on the edge of Olympus Mons, gazing at these rocks. Their surface is a mosaic of basalt, each grain a frozen snapshot from billions of years ago. The temperature here never rises above degrees Celsius, yet these stones carry memories warmer than any day in Antarctica's history. These magnetic signatures are so precise that scientists can determine the strength and orientation of Mars' ancient magnetic field with remarkable accuracy. The magnetic anomalies found on Mars are part of a global network created by the planet's past active core. On Earth, similar patterns have been used to reconstruct the movement and shape of tectonic plates. In contrast, Mars lacks plate tectonics, yet its magnetic field once spanned its entire globe, creating these unique geological signatures. This process occurred when Mars was geologically more active, with a molten core generating a dynamo effect. These rocks also serve as a reminder that life on both planets has been shaped by volcanic activity in profound ways. While Earth's volcanoes have built mountains and created islands, those on Mars once contributed to the planet's thin atmosphere and potential for water retention. Understanding this process allows us to appreciate how similar yet different our own planet's history might have been if conditions had varied slightly. The magnetic anomalies in Martian rocks highlight another fascinating aspect: their longevity. While Mars' surface has changed dramatically since its formation, these geological markers have remained relatively intact for billions of years. This durability is a stark contrast to Earth's more dynamic geology, where older rocks are often overwritten by newer formations. On Mars, the ancient magnetic signatures serve as a stable record, offering clues about conditions that existed long before our Sun stabilized into its current form. Moreover, these magnetic anomalies offer insights into the potential for past life on Mars. If volcanic activity could once support an atmosphere rich enough to retain heat and potentially sustain microbial life, then understanding these processes becomes crucial in the search for extraterrestrial biology. By studying Martian rocks, we can better understand how planets might have supported life elsewhere in the universe, and what conditions are necessary for life to emerge and thrive. As scientists analyze these magnetic signatures, they also consider their implications for future exploration of Mars. Understanding the planet's volcanic history could inform strategies for colonizing or mining resources from its surface. The iron-rich dust that covers these rocks not only provides clues about past geological activity, but also represents a potential resource for human settlers on the Red Planet. Extracting this iron could provide materials necessary for constructing habitats, tools, and even transportation systems. The study of magnetic anomalies on Mars raises questions about the long-term fate of our own planet. Earth's tectonic plates are constantly shifting, creating new land masses and subducting old ones into the mantle. This dynamic process is essential for maintaining a stable climate, but it also means that much of Earth's ancient geological history has been erased over time. In contrast, Mars' lack of plate tectonics allows its past to be preserved in ways we can barely comprehend from our active world. By exploring these magnetic anomalies on Mars, scientists gain a deeper understanding not only of the Red Planet, but also of Earth's own volcanic heritage. This knowledge helps us appreciate how both planets have evolved through time and offers insights into the potential for life elsewhere in the universe. Deep beneath the towering bulk of Olympus Mons, a geological phenomenon holds potential for transforming Mars into a sustainable habitat. At this Martian volcano's base, temperatures could rise above freezing point due to volcanic heat. This warmth is not evenly distributed across the planet. Instead, it concentrates in specific areas near ancient volcanoes and geothermal hotspots. Localized regions around these volcanic structures offer conditions that could sustain liquid water, an essential resource for future human colonization on Mars. These pockets of relative warmth are more than just anomalies. They represent potential sites for establishing self-sufficient colonies. The heat from these sources could be harnessed to melt subsurface ice, providing a reliable supply of water. To tap into this geothermal potential, scientists envision drilling deep beneath the Martian surface. This endeavor would require advanced technology capable of operating in extreme cold and thin atmosphere. These drills must navigate through layers of rock hardened by billions of years of cosmic bombardment. The equipment designed for such operations is robust enough to withstand the harsh conditions of Mars. The temperature differences between the Martian surface and its subsurface can be stark, with some regions as cold as a freezer, while others approach the freezing point at their warmest. This contrast underscores the complexity involved in extracting geothermal energy on Mars. It requires precise knowledge of where to drill and how to manage the equipment in such extreme conditions. Drilling into these hotspots presents risks beyond just technical challenges. The thin Martian atmosphere offers minimal protection against radiation, posing a constant threat to both human workers and sensitive machinery. Radiation levels can be as high as 25 rem per day on the surface, necessitating robust shielding for any operations near the surface. Despite these obstacles, the potential rewards of harnessing geothermal energy are significant. By tapping into this heat source, we could bring life-sustaining water to Mars' desolate landscapes. This endeavor would mark a monumental step in humanity's quest to expand beyond Earth, turning one of our solar system's most challenging environments into a home for future generations. The technology needed for such operations involves advanced materials capable of withstanding extreme cold, radiation exposure, and mechanical stress. These systems must also be designed for remote operation due to communication delays between Earth and Mars. The delay can reach up to 20 minutes each way, making real-time control impossible for many tasks. Innovations in drilling technology could lead to breakthroughs not just on Mars, but potentially elsewhere in the solar system. By mastering the art of extracting geothermal energy from distant worlds, we open doors to new frontiers of exploration and habitation. This vision stretches beyond merely sustaining human life. It envisions entire ecosystems thriving where none existed before. As scientists look towards harnessing Martian geothermal resources, they must consider the planet's long history of volcanic activity. These ancient eruptions have shaped the Martian landscape over billions of years, leaving behind a legacy of heat and minerals. Understanding this geological past is crucial for identifying optimal locations to drill. The iron in your blood was forged in stars that died before our sun existed, a reminder of how interconnected we are with the cosmos. Similarly, the materials found in Martian geothermal regions have their own cosmic histories. They tell stories of ancient stellar explosions and planetary formation, linking us not just to Mars, but to the broader universe. By exploring these connections, researchers can better predict where to find the most promising sites for tapping into Mars' hidden heat. This knowledge could lead to breakthroughs in energy extraction on other planets as well, expanding our reach across the solar system. Each discovery brings humanity closer to realizing its potential as a spacefaring species. The future of Martian exploration hinges on these geothermal hotspots, offering not only warmth, but also hope for sustained human presence. These areas are more than just points of heat. They represent gateways to new possibilities. As we delve deeper into Mars' subsurface, each drill bit turns up clues about the planet's past and potential future. The process of drilling on Mars is meticulous, with engineers carefully monitoring every step. Each meter drilled reveals layers of rock that have been untouched for eons. These layers hold secrets about Martian climate changes over time, offering insights into how the planet might evolve in the coming centuries or millennia. The data collected from these drills could help us understand not just Mars, but also Earth's own geological history. As we contemplate the future of human habitation on Mars, it becomes clear that geothermal energy is key to sustaining life there. Beyond providing warmth and water, this energy source could power habitats, grow crops in greenhouses, and even support manufacturing processes. The potential for self-sustaining colonies becomes more tangible with each successful extraction of heat from the Martian subsurface. The journey towards harnessing geothermal energy on Mars is not just a technological challenge, but also a testament to human ingenuity. It requires collaboration across disciplines, geologists, engineers, and scientists working together to unlock the secrets of this distant world. Each discovery brings us closer to understanding how life might one day thrive in environments once thought inhospitable. The first successful Mars rover, Sojourner, landed on July 4, 1997, marking the beginning of extensive robotic exploration. Since then, missions like Phoenix and InSight have provided valuable data about Martian soil composition and subsurface temperatures. These insights pave the way for future endeavors aimed at tapping into Mars' geothermal potential. As we continue to explore Mars, the red sands of Mars stretch endlessly under a thin veil of atmosphere, their hue a testament to iron oxide dust particles. Each grain bears the scars of countless micrometeorite impacts over eons, yet the landscape is not static. It shifts with the seasons. The Martian polar ice caps, however, remain a striking contrast in blue tones. These icy regions are primarily composed of frozen carbon dioxide, or dry ice, rather than water ice like Earth's poles. This unique blend of colors defines Mars' seasonal changes. As summer approaches at the planet's south pole, the surface temperature can rise to around -73 degrees Celsius, allowing the carbon dioxide ice to sublimate directly into gas without passing through a liquid phase. This process releases significant amounts of CO2 into the atmosphere, contributing to temporary warming effects. On Mars, this cycle underscores how different planets can follow similar orbital mechanics, yet manifest them in vastly distinct ways. The North Pole, however, differs slightly, with more water ice present due to its cooler temperatures and higher latitude. The Martian year, lasting approximately 687 Earth days due to its longer axial rotation and elliptical orbit, dictates the duration of these seasonal changes. During winter months at both poles, temperatures drop below -130 degrees Celsius, causing atmospheric CO2 to freeze onto the surface once more. This cycle is not just a visual change, but a dynamic process that reshapes Mars' atmosphere with each passing season. For comparison, this temperature would instantly frostbite human skin and render it inoperable within seconds of exposure, highlighting the extremity of conditions on the red planet. Mars' axial tilt of about 25 degrees is remarkably similar to Earth's 33 degrees. This similarity means that seasonal variations are somewhat analogous on both planets, yet the effects are dramatically different due to Mars' thinner atmosphere and greater distance from the Sun. The contrast between red sands and blue ice caps becomes particularly pronounced during polar summers, when the CO2 ice begins its annual sublimation process. In these moments, Mars reveals a complexity that belies its desolate appearance. Its seasons are not just temperature shifts, but dynamic processes involving the planet's very composition. During dust storms, which can envelop the entire globe for months at a time, the red dust obscures much of this seasonal beauty. These massive storms, driven by winds up to 160 kilometers per hour, significantly increase atmospheric pressure and redistribute dust particles across the planet, sometimes even altering surface reflectivity. This redistribution can disrupt the planet's seasonal balance for extended periods, affecting temperature gradients and wind patterns. The sublimation process at the poles also influences Mars' climate by altering atmospheric pressure and temperature distribution across the globe. This seasonal shift in CO2 levels can trigger regional dust storms and even affect global weather patterns. The polar regions, therefore, play a crucial role not just in defining seasons, but also in shaping the planet's overall environment. These processes highlight how interconnected and dynamic Mars truly is, despite its seemingly static appearance from afar. Olympus Mons, towering over the Martian plains, stands as a testament to Mars' volcanic past and its unique geological processes. With an elevation of 21.9 kilometers, this colossal mountain dwarfs Earth's Mount Everest by nearly 17 kilometers. On Mars, where plate tectonics are absent, a single volcanic vent remained active for millions of years, allowing lava to accumulate without interruption. At the base of Olympus Mons, each step you take covers more ground than on Earth due to Mars' lower gravity and thinner atmosphere. The surface gravity here is only 38% of Earth's, making every stride feel lighter, yet also posing challenges for maintaining bone density over time. This reduced gravitational pull affects not just movement, but also the way dust settles around the mountain, creating patterns that are unique to Mars. The volcano's immense size also influences local weather patterns and atmospheric circulation. Its shadowed regions remain cooler longer than sunlit plains, potentially preserving organic compounds that might otherwise degrade in warmer conditions. These areas could provide valuable data about Mars' habitability over time, especially during periods when the planet may have been more hospitable to life. One might wonder what it would be like to stand atop this Martian giant. The thin atmosphere means no clouds obscure the view, offering an unobstructed panorama of Mars' surface stretching endlessly toward the horizon. Yet, despite its grandeur, Olympus Mons exists in a state of eerie stillness, devoid of the wind and weather that shape Earth's landscapes. Even if you shouted from the summit, your voice would carry little distance before dissipating into the vacuum-like conditions above. The mountain's shadowed regions also offer unique environments for study. These areas remain cooler longer than sunlit plains, potentially preserving organic compounds that might otherwise degrade in warmer conditions. Such regions could provide valuable data about Mars' habitability over time, especially during periods when the planet may have been more hospitable to life. The extreme cold here can reach temperatures as low as -128 degrees Celsius, making it one of the coldest places on Mars. Understanding Olympus Mons is crucial not only for its scientific value, but also for what it represents: Mars as a dynamic world shaped by forces both internal and external. Its existence challenges our understanding of planetary formation and evolution, offering insights that could be applied to other celestial bodies in the solar system and beyond. The volcano's influence extends far beyond just height. Its mass creates a gravitational well that affects nearby areas, subtly altering the surface topography and influencing local weather patterns. Olympus Mons also provides insights into future human exploration of Mars. Its proximity to potential scientific resources means it could serve as a central location for future research stations or even colonies. However, reaching such heights would require advanced technologies capable of withstanding the extreme cold and thin atmosphere. The mountain's flanks might hold valuable information about Mars' past, including clues about potential water sources or signs of ancient volcanic activity that could have supported microbial life. The vastness of Olympus Mons extends far beyond just height. Its influence on Martian geology is profound. Its mass creates a gravitational well that affects nearby areas, subtly altering the surface topography and influencing local weather patterns by an estimated 0.2 millibars in pressure variation within a radius of 50 kilometers. Olympus Mons formation contrasts sharply with Earth's mountain-building processes, where plate tectonics play a pivotal role. The lack of this dynamic movement on Mars allowed for uninterrupted volcanic activity at a single site, resulting in an unparalleled monstrosity that defies comparison to any terrestrial feature. This prolonged activity created not just the height, but also the vast caldera atop Olympus Mons, which spans nearly 87 kilometers across. Interestingly, despite its massive size, Olympus Mons is not the only giant on Mars. It is part of a cluster of large volcanoes in Tharsis Montes, suggesting a period of intense volcanic activity that shaped much of the planet's surface. In addition to being an impressive geological formation, Olympus Mons has significant implications for Mars exploration strategies. Its proximity to potential scientific resources means it could serve as a central location for future research stations or even colonies. However, reaching such heights would require advanced technologies capable of withstanding the extreme cold and thin atmosphere. The mountain's shadowed regions also offer unique environments for study. These areas remain cooler longer than sunlit plains, potentially preserving organic compounds that might otherwise degrade in warmer conditions. Such regions could provide valuable data about Mars' habitability over time, especially during periods when the planet may have been more hospitable to life. The extreme cold here can reach temperatures as low as -128 degrees Celsius, making it one of the coldest places on Mars. The volcano's formation contrasts sharply with Earth's mountain-building processes, where plate tectonics play a pivotal role. The lack of this dynamic movement on Mars allowed for uninterrupted volcanic activity at a single site, resulting in an unparalleled monstrosity that defies comparison to any terrestrial feature. This prolonged activity created not just the height, but also the vast caldera atop. Millions of years ago, Mars was a planet where rivers and lakes once thrived, sculpting its surface with liquid water. These ancient waterways left behind extensive networks of channels, some as wide as 10 kilometers and deeply etched into the Martian crust. Each channel is a testament to the planet's dynamic history, where liquid water shaped landscapes with relentless force. Scientists have mapped thousands of these river channels, each one a snapshot of Mars' watery past. The sheer volume of water that flowed through them suggests rivers were active for millions of years, possibly even hosting microbial life forms in their depths. These ancient rivers carved out valleys and deposited sediments, much like the rivers on Earth today. Notably, these channels are often found near impact craters, suggesting that meteorite impacts may have played a role in creating reservoirs of underground water. The rivers likely originated from melting ice or underground aquifers, indicating that Mars once had a climate similar to Earth's, capable of sustaining liquid water on its surface. This period was crucial for potential life forms, which might have existed in these aquatic environments. The iron-rich minerals found along the riverbeds suggest that these waters were rich in nutrients, potentially supporting microbial life. Moreover, the presence of clay minerals indicates past interactions between water and rock, a process that could have provided habitats for early life. Imagine standing at the edge of one of these ancient riverbeds, where the water flows over smooth stones with an average velocity of about 1 meter per second, carrying sediment from the highlands to the lowlands. These rivers not only shaped the Martian surface, but also played a vital role in transporting nutrients that could have supported life. However, despite this seemingly hospitable environment, Mars' weaker sun back then meant that any potential life here had to adapt to lower light levels for photosynthesis. Over time, these active river systems transformed into dry river beds as Mars lost its atmosphere and became colder. Today, the remnants of these rivers lie beneath layers of dust and rock, preserved like fossils from a bygone era. Each layer of sediment tells a story about the planet's climate history, offering vital clues to how Mars evolved over billions of years. The patterns in these sediments suggest that Mars experienced cycles of wetness and dryness, much like Earth does during ice ages. The ancient rivers of Mars not only inform our understanding of Mars, but also provide insights into how planets can evolve from watery worlds to dry deserts over time. By studying these channels, scientists are uncovering pieces of the puzzle that will help us understand the potential for life on other worlds and the complex interplay between a planet's climate, geology, and its ability to sustain liquid water. The study of Martian river systems also offers parallels with Earth's own geological history, hinting at the universal processes that shape planetary surfaces. The ancient rivers of Mars not only shaped its surface, but also influenced the planet's atmosphere and climate in profound ways. As water flowed through these channels, it interacted with the thin Martian air, which was rich in carbon dioxide at that time. This interaction would have led to chemical reactions that could have altered the composition of the atmosphere, potentially creating a greenhouse effect that kept temperatures above freezing for extended periods. The presence of minerals like hematite and jarosite along these riverbeds further supports this theory, as they are typically formed through long-term exposure to water. Moreover, these rivers help transport sediments from higher elevations to lower plains, gradually building up layers that would later become part of the Martian crust. The sedimentary rock formations found near ancient river channels provide evidence of this process, offering a glimpse into how Mars' surface was shaped over time. These deposits also contain clues about the types of environments that existed billions of years ago, such as shallow lakes or deltas, where water might have pooled and stagnated. Each layer of these sedimentary rocks tells a story of Martian history, from the earliest epochs when liquid water flowed freely to the later stages, when Mars began its transition into the cold, dry planet we see today. By studying these layers, scientists can piece together a timeline of how Mars lost its atmosphere and became colder, leading to the eventual disappearance of surface water. The ancient rivers of Mars are not just remnants of past geological activity. They are time capsules that hold the key to understanding the red planet's evolution over billions of years. However, an unexpected discovery is that some of these riverbeds show signs of flash flooding events, indicating sudden and intense bursts of water flow that could have been triggered by volcanic eruptions or massive meteorite impacts, adding complexity to Mars' watery past. Oxygen adaptation on Mars involves more than just adjusting to lower levels. It is an evolutionary challenge that spans generations. In the Martian atmosphere, where oxygen comprises only 13 parts per thousand compared to Earth's 21%, human lungs must work much harder to extract what little air they can. Each breath taken here would be similar to ascending Mount Everest, a feat where atmospheric pressure drops so significantly that even well-trained athletes struggle. The body compensates by producing more red blood cells and increasing the number of hemoglobin molecules in these cells to carry oxygen more efficiently. However, this adaptation process takes time, weeks or months for initial acclimatization, and can lead to chronic hypoxia if not managed properly. Over generations, humans might develop genetic variations that enhance their ability to extract oxygen from thin air, much like high-altitude natives on Earth who have adapted over millennia. While oxygen deprivation poses significant health risks, Martian settlers could potentially leverage biotechnology and gene editing to accelerate adaptation. Gene therapy or selective breeding might help future generations grow more efficient lungs and heart muscles capable of sustaining life with less available oxygen. Yet, even as technology advances, the biological clock remains relentless. Full adaptation through natural selection would still take countless years. This slow process underscores the complexity of human biology in adapting to new environments. Another critical factor is bone density and muscle mass due to reduced gravity on Mars, just 38% of Earth's. Over time, this could lead to weakened skeletal structures if not counteracted through rigorous exercise or artificial gravity environments. However, these physical changes might also provide an unexpected benefit: reduced energy expenditure in daily activities. This lower metabolic demand could allow settlers to allocate more resources towards other essential functions, such as cognitive processing and immune system maintenance. Epigenetics, the chemical modifications that affect gene expression without altering DNA sequence itself, plays a crucial role in adaptation on Mars. These modifications can be influenced by environmental factors and passed down through generations. On Mars, Where conditions are extreme and harsh, these changes could accumulate rapidly, potentially leading to a faster rate of adaptation than traditional genetic mutations might allow. This means that within just a few generations, the descendants of early colonists might already show significant physiological differences tailored for Martian life. The psychological impact of living in such an isolated environment should not be overlooked either. The sense of isolation and confinement could lead to unique mental adaptations or challenges. Over time, settlers might develop stronger social bonds and more resilient mental health strategies as they cope with the pressures of long-term space habitation. This psychological adaptation would be just as crucial for survival as any physical change, shaping a new form of human existence that is better equipped to thrive in alien environments. In conclusion, adapting to Mars over generations involves not only physiological changes, but also psychological and epigenetic transformations. These adaptations will redefine what it means to be human, creating a species capable of thriving in two distinct worlds, Earth and Mars. This evolutionary journey highlights the profound resilience and adaptability of life itself, pushing the boundaries of human potential far beyond our home planet. Martian soil is a complex mixture of minerals and reactive compounds that make it toxic for many Earth plants. Perchlorates, potent oxidizers, are abundant on the surface, reacting with water vapor in the thin Martian atmosphere to form hydrogen peroxide. This chemical interaction renders much of the soil inhospitable to plant life as we know it. The average temperature on Mars hovers around degrees Celsius, colder than even Antarctica's warmest days. In such extreme cold, liquid water cannot persist for long. Any moisture sublimates directly into vapor due to low atmospheric pressure. This process not only complicates efforts to grow plants, but also poses challenges for human habitation on the red planet. Martian dust particles are electrically charged because of solar wind stripping away electrons from their surfaces. These charged grains attract each other, leading to powerful electrostatic storms that can cover the entire globe. The same charge that causes balloons to stick to hair on Earth leads to massive dust clouds on Mars, capable of disrupting communications and damaging equipment. Surprisingly, while Mars is often considered an inhospitable wasteland, it may hold clues about life's adaptability. Certain extremophiles, organisms adapted to extreme conditions, thrive in environments with high salt concentrations or perchlorates. These microorganisms break down harmful compounds into less toxic substances, offering hope for potential bioremediation techniques on Mars. Efforts to grow plants on Mars must account not only for the toxicity of its soil, but also for the lack of a stable atmosphere and constant dust storms. Researchers are exploring ways to genetically engineer plants that can withstand these conditions, much like how crops are adapted for Earth's varying climates. These engineered plants could be key to establishing sustainable agriculture on the red planet. Understanding the atomic interactions in Martian soil is crucial for any future colonization efforts. By studying how plants might adapt or be engineered to survive in such an environment, we may unlock secrets that extend beyond Mars itself. This knowledge could help us understand life's potential elsewhere in the universe and guide our approach to terraforming other worlds. Toxic Martian thus not only poses immediate threats, but also presents long-term challenges for any sustained human presence on the planet. The fine particles, often finer than talcum powder, are easily inhaled and can cause respiratory issues if inhaled by astronauts or settlers. These tiny grains can infiltrate even the most advanced filtration systems, making it essential to develop robust protective measures for habitats and equipment. Moreover, the dust's abrasive nature wears down surfaces over time, accelerating the degradation of machinery and infrastructure. This wear is exacerbated by the frequent dust storms that can blanket entire regions in fine particulates. These storms, which can last for months and span continents, are not just a nuisance, but a significant hazard to both equipment and human health. Despite these obstacles, there is hope. Scientists are investigating how to harness the very properties of Martian soil that make it toxic. For instance, perchlorates could potentially be used as a source of oxygen or fuel if they can be safely extracted and processed. This would require innovative engineering solutions to manage the risks while extracting valuable resources from this hostile environment. The study of Martian dust also provides insights into Earth's own geological processes. The way particles interact on Mars mirrors some of the early stages of planetary formation, offering a glimpse into how our own planet might have evolved billions of years ago. This comparative analysis is crucial for understanding the broader context of life and habitability across different worlds. By addressing the toxicity of Martian soil, we are also paving the way for future exploration and potential habitation. Each challenge encountered on Mars brings us closer to unraveling the mysteries of our solar system and beyond, guiding us towards a deeper understanding of what it means to live in environments vastly different from Earth's familiar conditions. Detecting faint magnetic fields on Mars is like uncovering traces of its ancient core activity. These remnants suggest a time when Mars had an active dynamo, similar to Earth's current magnetosphere. The strength of these fields varies widely across the Martian surface, with some areas displaying stronger signals than others. This variability indicates complex geological processes and internal heat flow that once shaped the planet's magnetic field. In particular, regions like Tharsis and Arabia display enhanced magnetic signals, suggesting intense volcanic activity in the distant past. These instruments are exquisitely sensitive, capable of detecting fields as weak as 1% of Earth's strength. This precision allows scientists to map out specific areas where remnants of Mars' ancient dynamo persist, offering a detailed view of its geological history. The data collected can reveal how Mars transitioned from an active geophysical body to the cold, dormant world we observe today. Understanding these magnetic fields also provides clues about Mars' potential for supporting life in the past or future. A strong magnetic field would have shielded the planet's surface from harmful solar and cosmic radiation, possibly allowing conditions more conducive to life. This protective effect is crucial when considering the viability of human colonization on Mars. The same processes that shaped Mars' core billions of years ago also influenced Earth's geological history. Studying these remnants allows us to better understand our own planet's past and future. Moreover, the detection of these ancient magnetic fields has broader implications beyond just Mars. By mapping out these fields, scientists can identify areas with higher concentrations of valuable resources like metals and water ice. These locations could be prime spots for establishing bases or mining operations should humanity ever attempt to inhabit Mars. The instruments used to detect these magnetic fields on Mars are marvels of engineering, designed to withstand the harsh Martian environment. They must function in temperatures as low as -63 degrees Celsius and endure dust storms that can last for months. For instance, some sensors have been known to malfunction due to prolonged exposure to fine Martian dust, highlighting the challenges faced by engineers in maintaining these delicate instruments. The magnetic signals detected on Mars reveal how volcanic activity once heated regions up to 50 kilometers below the surface, leading to the formation of features like Olympus Mons. These massive volcanoes were once powered by an active core, producing lava flows that shaped the landscape. Each measurement contributes to a larger picture of Mars' geophysical past, revealing how its internal processes have shaped its surface over billions of years. In essence, these faint magnetic fields serve as a bridge between Mars' ancient past and its future possibilities. They inform us about the planet's internal dynamics, potential for life, and even its role in broader cosmic contexts. As we continue to explore Mars, these signals will remain crucial guides, helping us unravel the mysteries of this red world. Detecting faint magnetic fields on Mars is like uncovering traces of its ancient core activity. These remnants suggest a time when Mars had an active dynamo, similar to Earth's current magnetosphere. The strength of these fields varies widely across the Martian surface, with some areas displaying stronger signals than others. This variability indicates complex geological processes and internal heat flow that once shaped the planet's magnetic field. In particular, regions like Tharsis and Arabia display enhanced magnetic signals, suggesting intense volcanic activity in the distant past. These instruments are exquisitely sensitive, capable of detecting fields as weak as 1% of Earth's strength. This precision allows scientists to map out specific areas where remnants of Mars' ancient dynamo persist, offering a detailed view of its geological history. The data collected can reveal how Mars transitioned from an active geophysical body to the cold, dormant world we observe today. Understanding these magnetic fields also provides clues about Mars' potential for supporting life in the past or future. A strong magnetic field would have shielded the planet's surface from harmful solar and cosmic radiation, possibly allowing conditions more conducive to life. This protective effect is crucial when considering the viability of human colonization on Mars. The same processes that shaped Mars' core billions of years ago also influenced Earth's geological history. Studying these remnants allows us to better understand our own planet's past and future. Moreover, the detection of these ancient magnetic fields has broader implications beyond just Mars. By mapping out these fields, scientists can identify areas with higher concentrations of valuable resources like metals and water ice. These locations could be prime spots for establishing bases or mining operations, should humanity ever attempt to inhabit Mars. The instruments used to detect these magnetic fields on Mars are marvels of engineering, designed to withstand the harsh Martian environment. They must function in temperatures as low as -63 degrees Celsius and endure dust storms that can last for months. The magnetic signals detected on Mars reveal how volcanic activity once heated regions up to 50 kilometers below the surface, leading to the formation of features like Olympus Mons. These massive volcanoes were once powered by an active core, producing lava flows that shaped the landscape. Each measurement contributes to a larger picture of Mars' geophysical past, revealing how its internal processes have shaped its surface over billions of years. In essence, these faint magnetic fields serve as a bridge between Mars' ancient past and its future possibilities. They inform us about the planet's internal dynamics, potential for life, and even its role in broader cosmic contexts. As we continue to explore Mars, these signals will remain crucial guides, helping us unravel the mysteries of this red world. Dust devils on Mars are not mere atmospheric disturbances. They are intricate whirlwinds shaped by the planet's thin atmosphere and cold temperatures. These vortices can grow to be as wide as a football field and reach heights of up to 10 kilometers, spinning with winds that can exceed 100 kilometers per hour. The Martian surface, covered in fine dust particles, provides an ideal medium for these whirlwinds to form and move across the landscape. Each dust devil is a unique event, influenced by local conditions such as temperature gradients and wind patterns. The process begins when sunlight heats patches of ground unevenly, causing pockets of air to rise more quickly than others. This creates small vortices that can merge into larger whirlwinds under the right conditions. On Mars, where the atmosphere is 100 times thinner than Earth's, these dust devils can grow much larger and persist for longer periods. The thinness of the Martian atmosphere means less friction to slow them down, allowing them to maintain their energy over greater distances. What makes Martian dust devils particularly fascinating is their ability to uncover ancient particles buried beneath the surface. As they sweep across the red plains, these whirlwinds can lift and redistribute material that has been untouched for billions of years. This process acts as a natural exfoliation, revealing layers of regolith that have accumulated over time. Each dust devil carries with it a story of Mars' past, stirring up particles that could hold clues to the planet's geological history. Unlike Earth, where water vapor plays a crucial role in forming whirlwinds, Martian dust devils rely solely on the movement of dry particulates. The low atmospheric pressure on Mars means that liquid water cannot exist freely for long periods, and even ice sublimates directly into gas under these conditions. This unique environment allows for the formation of massive dust devils without the need for moisture, a process that would be impossible in Earth's more humid atmosphere. Dust devils also play a significant role in redistributing iron-rich dust across Mars' surface. The red hue we associate with Mars is due to the presence of iron oxide particles, which are lifted and deposited by these whirlwinds. This continuous movement helps maintain the planet's characteristic coloration and contributes to its distinctive appearance from space. Each dust devil acts as a conveyor belt, transporting materials over vast distances and contributing to the homogenization of Martian soil. The study of these phenomena provides valuable insights into the broader dynamics of Mars' atmosphere and surface interactions. By tracking the paths of dust devils, scientists can better understand how material is distributed across the planet's surface and how it changes over time. This information is crucial for future missions aiming to explore and potentially settle on Mars, as understanding these processes will be key to developing sustainable habitats in this harsh environment. Dust devils also influence the Martian climate by redistributing heat across the surface. As they rise and fall, these whirlwinds carry warm air from sunlit areas to cooler regions, creating a complex pattern of thermal circulation. This process is particularly pronounced during the planet's warmer seasons, when temperature differences between day and night are more extreme. The resulting atmospheric mixing can have far-reaching effects on weather patterns, influencing everything from dust storms to localized changes in surface temperature. On Earth, similar whirlwinds occur, but are typically much smaller and less frequent due to a denser atmosphere that provides more friction to dissipate energy. In contrast, Mars' thin air allows these vortices to grow larger and persist longer, making them a dominant feature of the planet's dynamic landscape. The longevity of Martian dust devils means they can travel vast distances, sometimes covering hundreds of kilometers in a single day. This extensive movement helps to homogenize the surface temperature across wide areas, smoothing out extreme variations caused by uneven heating. These whirlwinds also play a role in shaping the Martian environment over geological timescales. By constantly stirring up and redepositing material, dust devils contribute to the erosion and deposition processes that sculpt the planet's surface. This ongoing activity helps maintain the dynamic balance between wind-driven changes and more gradual geological forces like volcanic activity or meteorite impacts. Each dust devil is a fleeting yet significant event in this continuous process of planetary reshaping. Understanding the behavior of dust devils on Mars is essential for future exploration efforts, as they can pose both challenges and opportunities for surface operations. For instance, the swirling winds could disrupt sensitive equipment or even cause temporary power outages if solar panels are obscured by lifted dust. However, these whirlwinds also offer a unique opportunity to study Martian atmospheric dynamics up close. By analyzing the composition of particles carried aloft, scientists can gain valuable insights into the chemical makeup of different regions on Mars. Moreover, the paths left behind. Mars' axial tilt varies over millions of years, a cycle that profoundly influences its climate and atmosphere. This variation is not just a local phenomenon, but has surprising connections to Earth's own climate patterns through orbital mechanics. The tilt of Mars ranges from about 15 degrees to nearly 35 degrees, affecting the distribution of sunlight across the planet's surface. During periods of higher axial tilt, Mars experiences more extreme seasonal changes, with warmer summers and colder winters. This cycle can last for tens of thousands of years, significantly altering the planet's climate over time. On Earth, similar variations in axial tilt have been linked to ice ages and interglacial periods, demonstrating how small shifts in orbital parameters can drive major climatic events. The Sun's energy reaching Mars during these high-tilt phases is more than 50% concentrated at the poles, leading to greater seasonal contrasts. Mars' thin atmosphere, composed mostly of carbon dioxide, plays a crucial role in this process. As the tilt changes, so does the pressure and composition of the atmosphere, influencing how much heat is retained or lost. This dynamic interplay between axial tilt and atmospheric conditions on Mars mirrors Earth's greenhouse effect, though on a vastly different scale. On Earth, variations in axial tilt have been implicated in the formation of ice ages due to altered sunlight distribution. The Martian surface gravity is only 38% of Earth's, which affects how dust storms form and propagate across the planet. During periods of higher tilt, increased wind speeds can lead to more frequent and intense dust storms. These storms not only obscure the landscape, but also redistribute heat across Mars, creating temporary warm spots in otherwise frigid regions. The energy generated by these storms is remarkable, often surpassing what direct sunlight provides on a calm day. Despite its cold average temperature of -63 degrees Celsius, Mars can experience localized warming during dust storm events. These storms are not just atmospheric disturbances, but intricate whirlwinds shaped by the planet's thin atmosphere and cold temperatures. The energy dynamics involved in these storms highlight how natural processes can create unexpected conditions even in harsh environments, much like Earth's desert regions, where intense heat can arise from wind-driven sand. However, during particularly severe dust storms, Mars' surface temperature can spike up to 35 degrees Celsius temporarily, a dramatic shift that challenges our understanding of the planet's thermal dynamics. Understanding Mars' axial tilt variations offers insights into its past and future climate states. These cycles have likely influenced the planet's ability to retain a thicker atmosphere or sustain liquid water on its surface at various points in history. By studying these patterns, scientists gain a deeper understanding of how orbital mechanics can shape planetary climates over geological timescales, offering parallels that extend beyond Mars to Earth and other planets within our solar system. Mars' axial tilt variations also affect its magnetic field, or rather, the lack thereof. Unlike Earth, which has a robust magnetic shield generated by an active dynamo in its core, Mars lacks such a protective mechanism due to its smaller size and cooler interior. This absence of a strong magnetic field means that Mars is more vulnerable to solar winds and cosmic radiation, stripping away any atmosphere it once had. During periods when Mars tilts more dramatically, the polar regions receive significantly more sunlight. This increased exposure can lead to the sublimation of carbon dioxide ice at the poles, further thinning the already sparse Martian atmosphere. The process is cyclical. As the tilt changes back towards lower angles, the poles cool again and carbon dioxide refreezes, potentially replenishing atmospheric pressure in a slow and delicate balance. This cycle underscores how Mars' climate is tightly coupled with its orbital mechanics. Much like Earth's seasonal variations are tied to its axial tilt. The thinning of Mars' atmosphere during high tilt periods also impacts the planet's ability to retain heat. Without a thick layer of gases to trap warmth, any localized heating from dust storms or other sources dissipates quickly into space. This rapid cooling highlights the tenuous nature of Mars' environment and how finely balanced its climate systems are. On Earth, greenhouse gases help maintain surface temperatures, but Mars lacks such stabilizing factors, making it a stark example of what happens when planetary climates are left unchecked by protective atmospheric layers. These variations in axial tilt have likely played a crucial role in the evolution of Mars' atmosphere over billions of years. The planet's history is marked by periods where it may have had more substantial water and a thicker atmosphere, only to lose them as its tilt changed and solar winds eroded what little remained. Understanding these cycles provides valuable context for future exploration missions, offering clues about past habitability and the potential for sustaining human life on Mars in the distant future. 4 billion years ago, Mars underwent a critical transformation when its magnetic field ceased to exist. This precise moment marked the end of an internal dynamo that once generated protective fields against solar winds and cosmic radiation. Without this shield, the planet became increasingly exposed, leading to significant atmospheric erosion over time. The loss of the magnetic field was not instantaneous, but occurred gradually as Mars' core cooled and solidified, leaving behind only faint traces of its former strength. This event altered the course of Martian history forever, setting the stage for the cold, thin atmosphere we observe today. The exact moment when Mars lost its magnetic field is difficult to pinpoint precisely, but it likely occurred around 4.2 billion years ago. At this time, Mars was still relatively young and active geologically, with a molten core that generated a strong protective shield. However, as the planet cooled, its internal dynamo weakened until it finally ceased. This cessation had profound implications for Mars' atmosphere, leading to the loss of much of its early water vapor and carbon dioxide. The thinning atmosphere allowed solar radiation to strip away lighter molecules from the upper layers, leaving behind a cold, dry world where liquid water could not persist on the surface. Today, remnants of this ancient magnetic field can be detected in certain regions of Mars through faint anomalies in the planet's crust. These anomalies are like echoes of a time when Mars had an active dynamo, similar to Earth's current magnetosphere. However, unlike Earth, these traces are insufficient to protect Mars from the harsh solar winds that continue to bombard its surface. The absence of this protective field means that any future human exploration or settlement on Mars will require artificial shielding against radiation and a carefully managed atmosphere within pressurized habitats. The loss of Mars' magnetic field has also influenced the planet's climate in ways that are still not fully understood. Without the shield, cosmic rays and solar wind particles can penetrate deeper into the Martian atmosphere, potentially influencing cloud formation and atmospheric circulation patterns. This interaction between ancient geology and current climate dynamics adds another layer to our understanding of how Mars became the cold, dry world it is today. It also raises questions about the potential for future changes in the planet's environment if human activities were to alter its surface or introduce new materials. For instance, some scientists speculate that introducing magnetic fields artificially could lead to unexpected weather patterns on Mars, such as more frequent dust storms or altered wind speeds. In contrast to the vastness of interstellar space, where magnetic fields can extend for light years, the remnants of Mars' ancient field are confined to localized areas on its surface. These anomalies provide scientists with valuable clues about the internal structure and thermal history of the planet. They also highlight the delicate balance between a planet's geology and its ability to maintain an atmosphere capable of supporting life as we know it. The study of these magnetic traces is crucial for understanding not only Mars, but also other planets in our solar system, including Earth, which continues to benefit from its protective magnetosphere. Specifically, scientists have mapped out areas where the magnetic field anomalies reach strengths up to 10 microteslas, providing insights into how Mars' core cooled and solidified over time. The implications of Mars losing its magnetic field extend far beyond the planet itself. It serves as a reminder that even small changes in planetary conditions can have long-lasting effects on habitability. For instance, if Earth were to lose its magnetic field, it would face similar challenges with radiation exposure and atmospheric loss. This connection underscores the importance of studying Mars, not just for its own sake, but also as a cautionary tale about the fragility of environments that support life. As we continue to explore Mars, each discovery brings us closer to understanding both our past and future on this distant world. In this harsh environment, the contrast between the cold deserts and the comparatively warm volcanic regions becomes striking. The temperature difference can be as much as 100 degrees Celsius near active volcanic vents. This temperature gradient plays a significant role in atmospheric circulation patterns around Mars, influencing dust storms and wind dynamics. For humans, such dramatic shifts would require highly adaptive spacesuits capable of withstanding both extreme cold and localized heat sources. In areas where volcanic plains meet deserts, the reduced gravity can alter how dust moves and settles. Sand dunes near volcanic vents might shift more slowly due to lower wind speeds caused by the gravitational differences. This subtle change in sediment movement reflects a profound difference between Mars and Earth, highlighting the unique challenges faced by any potential human settlers. The surface gravity on Mars is only 38% that of Earth's, which affects how these environments interact. Dust storms on Mars are another factor that shapes this boundary zone. These colossal storms can cover vast areas of the planet for months at a time, with winds reaching up to 160 kilometers h. As these storms sweep across the desert volcano interface, they redistribute dust and volcanic particles, creating new layers of sediment that record the passage of time. The iron-rich dust interacts chemically with volcanic gases, potentially enriching the soil near the boundary in ways that could be crucial for future exploration or colonization efforts. Martian deserts and volcanic plains also interact through their respective magnetic signatures. While much of Mars lacks a global magnetic field due to its inactive core, localized anomalies are detectable at these boundaries. These remnants suggest ancient processes when Mars had an active dynamo similar to Earth's current magnetosphere. For scientists studying Mars, understanding these local magnetic fields provides insights into both the planet's volcanic history and potential pathways for future resource extraction. As night falls on this distant world, the boundary between desert and volcano remains a dynamic frontier where geological forces continue their silent choreography. The low-hanging sun casts long shadows across the terrain, revealing subtle textures in the dust that could take millions of years to change. In this isolated environment, time stretches out, offering a glimpse into both the ancient past and the uncertain future of Mars. This boundary zone is not just a physical division, but also a witness to the planet's evolution over billions of years. The interaction between these two environments is further influenced by seasonal changes on Mars. During Martian spring and summer, increased solar radiation can heat up the volcanic plains, causing localized warming that affects nearby desert regions. This heating process can trigger dust storms and alter the chemical composition of the surface materials. These seasonal variations underscore how interconnected the different parts of Mars truly are, despite their stark contrasts. At this boundary, the contrast between the two environments is striking yet delicate. The volcanic plains, with their dark basaltic rock and smooth, wind-polished surfaces, sit in stark relief against the bright red dunes of the desert. This juxtaposition creates a visual tension that mirrors the geological processes at play beneath the surface. Over millennia, these landscapes have shaped each other through erosion and deposition, creating unique features such as volcanic sand dunes formed from ash particles and wind-sculpted rock formations. The interaction between these contrasting terrains is not static. It evolves with every gust of wind, every dust particle that settles, and every tremor beneath the surface. The temperature differences at this interface are also significant. While the desert can experience dramatic swings in temperature, the volcanic plains tend to retain heat longer due to their darker coloration and higher thermal conductivity. This creates microclimates where the immediate environment around a vent or fissure might be warmer than the surrounding desert by several degrees. These localized variations can create unique habitats for extremophile organisms that might one day be discovered on Mars, offering clues about potential life beyond Earth. The temperature gradient at this boundary zone is not just a matter of comfort for hypothetical future colonists. It could also provide valuable information about the planet's thermal history and current geothermal activity. Water plays a subtle yet crucial role in these interactions, despite its scarcity on Mars. In certain areas near volcanic features, subsurface water ice can be partially melted by heat from below, creating temporary wet spots that alter the soil chemistry and contribute to the formation of clay minerals. These transient moisture events are fleeting but significant, as they offer potential oases for microbial life or resources for future exploration missions. The presence of such ephemeral water sources at this boundary underscores the complexity of Mars' surface processes and highlights the dynamic interplay between geological features. The dust storms that periodically engulf Mars also have a profound effect on this boundary zone, as the integration of human-made habitats with Mars' surface over decades is a complex process involving continuous adaptation and innovation. Each new challenge encountered leads to advancements that push the boundaries of what we can achieve on this distant world. This ongoing evolution not only ensures survival, but also deepens our understanding of Mars itself. Communication delays between Earth and Mars, averaging around 20 minutes each way, pose unique challenges for mission control. Over decades, habitats will need to become more autonomous, capable of managing day-to-day operations independently without constant oversight from ground crews. This shift toward greater self-sufficiency is crucial for the long-term sustainability of any settlement. The surface gravity on Mars is only 38% of Earth's, making every step feel lighter, but also leading to concerns about bone density loss over time. To mitigate this, habitats will incorporate artificial gravity systems or exercise regimes that simulate higher gravitational forces. These measures aim to maintain astronauts' physical health and prevent the long-term effects of reduced gravity. Mars' atmosphere contains only 0.13% oxygen compared to Earth's 21%, posing significant challenges for human respiration. Over time, habitats will need sophisticated life support systems capable of extracting and recycling limited resources. These systems are not just about survival, but also about creating a sustainable environment where humans can thrive. The Martian dust storms can cover the entire planet and last for months, with winds reaching up to 160 kilometers/h. To protect against these powerful forces, habitats will be built with robust sealing mechanisms and protective layers. These structures must withstand not only high wind speeds, but also the abrasive nature of Martian dust. Over decades, habitats on Mars will evolve into integrated systems that blend technology with the planet's unique environment. This process involves more than just building shelters. It requires a deep understanding of how to live in harmony with Mars' harsh conditions. Each new generation of habitat design builds upon previous knowledge, creating a legacy of innovation and resilience. The integration of human-made habitats with Mars' surface over decades is a complex process involving continuous adaptation and innovation. Each new challenge encountered leads to advancements that push the boundaries of what we can achieve on this distant world. This ongoing evolution not only ensures survival, but also deepens our understanding of Mars itself. Communication delays between Earth and Mars, averaging around 20 minutes each way, pose unique challenges for mission control. Over decades, habitats will need to become more autonomous, capable of managing day-to-day operations independently without constant oversight from ground crews. This shift toward greater self-sufficiency is crucial for the long-term sustainability of any settlement. The surface gravity on Mars is only 38% of Earth's, making every step feel lighter, but also leading to concerns about bone density loss over time. To mitigate this, habitats will incorporate artificial gravity systems or exercise regimes that simulate higher gravitational forces. These measures aim to maintain astronauts' physical health and prevent the long-term effects of reduced gravity. Mars' atmosphere contains only 0.13% oxygen compared to Earth's 21%, posing significant challenges for human respiration. Over time, habitats will need sophisticated life support systems capable of extracting and recycling limited resources. These systems are not just about survival, but also about creating a sustainable environment where humans can thrive. The Martian dust storms can cover the entire planet and last for months, with winds reaching up to 160 km/h to protect against these powerful forces. Habitats will be built with robust sealing mechanisms and protective layers. These structures must withstand not only high wind speeds, but also the abrasive nature of Martian dust. Over time, habitats on Mars will incorporate features that enhance psychological well-being in isolation. For instance, internal spaces might simulate Earth-like environments to provide a sense of familiarity and comfort. Lighting systems could mimic natural daylight cycles, helping astronauts maintain circadian rhythms despite the longer Martian day. These small touches are crucial for maintaining mental health overextended. In this silent world, sound travels only if carried by minute dust particles kicked up by wind or movement. These tiny grains might convey faint pressure waves over short distances, but the vast majority of potential noise simply cannot exist due to the thin air. The absence of audible cues creates a unique sensory environment where visual information becomes paramount for survival and exploration. As humans adapt to living in this silent world, they will learn to interpret their surroundings through other means, developing new ways to navigate and communicate in a landscape dominated by sight rather than sound. The Martian atmosphere is so thin that it exerts only about 0.6% of the pressure at sea level on Earth. This makes Mars an almost airless environment where even the loudest human voice would be inaudible beyond a few meters. In contrast, on Earth, sound can travel for kilometers under ideal conditions, yet on Mars, any noise is quickly swallowed by the vacuum. The silence here is absolute, save for occasional dust storms that stir up particles and create brief, low-frequency rumbles. Imagine standing near the base of Olympus Mons, the tallest volcano in the solar system. At 21.9 kilometers high, it dwarfs Earth's Mount Everest by nearly 17 kilometers. Despite its monumental size, the silence at this location is profound. The thin air means that even a massive eruption would produce little more than faint pressure waves, barely detectable over short distances. This paradoxical quiet, in such an active geological setting, underscores the unique challenges of sound propagation on Mars. The cold temperatures on Mars, averaging -63 degrees Celsius, further complicate the transmission of sound. At these frigid conditions, air molecules are less energetic and move more slowly, reducing their ability to carry sound waves effectively. The extreme cold also causes water vapor in the atmosphere to condense or freeze immediately upon contact with surfaces, eliminating another potential source of noise from droplets or ice formation. In this silent world, communication between astronauts or robotic explorers would depend entirely on radio signals, which travel through the vacuum without interference from sound. These signals can take up to 20 minutes each way when Mars is at its farthest point from Earth, creating a significant delay in real-time interaction. This lag introduces challenges for mission control and remote operations, but also highlights the necessity of autonomous systems capable of operating independently on Mars. Despite the silence, there are moments where sound could theoretically exist, during dust storms or when particles collide with each other. These brief instances of noise would be fleeting and low frequency, offering a stark contrast to the usual quietude. The experience of hearing these rare sounds might feel surreal for astronauts accustomed to the constant hum of life support systems within their habitats. Yet, even in these moments, the overall environment remains profoundly silent. Consider the experience of sound on Mars through human ears. If an astronaut were to shout at the top of their lungs, the pressure waves would dissipate almost instantly due to the lack of atmospheric density. In this environment, the human voice serves little purpose for communication beyond immediate proximity. Instead, astronauts must rely on visual signals and electronic devices designed specifically for low-pressure environments. These tools are crucial not only for survival, but also for maintaining a sense of connection in an otherwise isolating silence. The thin Martian atmosphere also affects how we might perceive sound if it were present. On Earth, our ears can detect frequencies ranging from about 20 to 20,000 hertz. However, on Mars, the limited air pressure would restrict audible sounds to a much narrower range, primarily low-frequency rumbles and vibrations. This limitation means that even if there were sources of noise, such as dust storms or equipment malfunctions, they would be perceived differently than on Earth. The silence here is not just an absence of sound, but also a distortion of how we experience auditory stimuli. Moreover, the unique conditions on Mars can lead to unexpected phenomena related to sound. For instance, during certain atmospheric events like dust devils or localized pressure changes, there could be brief instances where sound waves might propagate over short distances. These rare occurrences would create an eerie contrast against the usual silence, potentially offering moments of auditory surprise for those exploring the Martian surface. Yet, these fleeting sounds are far from the continuous background noise we take for granted on Earth. The absence of sound on Mars also has implications for human physiology and psychology. The prolonged exposure to such profound quiet could lead to sensory deprivation, affecting cognitive functions and emotional well-being. To mitigate this, future missions might incorporate artificial soundscapes within habitats or use technology that simulates familiar auditory environments from Earth. These measures would help maintain astronauts' mental health while they adapt to the unique challenges of living on a silent world. The red dust that blankets Mars is not a passive residue of time. It is an ongoing product of cosmic violence, each grain sculpted from micrometeorite impacts over billions of years. On this distant world, silence is absolute. There are no molecules to carry sound through its thin atmosphere, yet it is bombarded incessantly by particles from space. This bombardment contributes not only to the surface's constant reshaping, but also to the erosion of Mars' already tenuous atmosphere. Solar radiation continuously strips away atoms and molecules from Mars' upper atmosphere, a process known as solar wind stripping. This phenomenon gradually depletes the planet's atmospheric gases, including carbon dioxide and argon. Over billions of years, this relentless extraction could leave Mars with an even thinner atmosphere than it has today, further reducing its ability to retain heat or water vapor. Mars' surface gravity is only 38% of Earth's, meaning objects weigh less here, but also experience reduced bone density over time for any human inhabitants. This lighter environment affects not just the physical exertion required, but also the potential for long-term health issues such as osteoporosis and muscle atrophy. The thin atmosphere provides little protection against radiation, which could exacerbate these challenges. The dust storms on Mars are a significant factor in the planet's atmospheric dynamics. These colossal storms can cover the entire planet and last for months, with winds reaching up to 160 kilometers per hour. As they rage across the surface, these storms stir up fine particles that scatter sunlight, creating an almost perpetual twilight over large areas of Mars. This constant stirring further accelerates the erosion of the thin atmosphere by exposing more material to solar radiation. Deep beneath the Martian soil lies a history of volcanic activity that shaped much of its surface. The presence of vast lava plains and towering volcanoes like Olympus Mons indicates periods when Mars was geologically active, spewing gases into the atmosphere. However, as these processes have slowed over time, so too has the replenishment of atmospheric gases, contributing to the gradual thinning observed today. In the distant future, if solar radiation continues to strip away Mars' atmosphere entirely, the planet will become an even harsher environment for any potential life forms or human settlers. The surface will be exposed directly to cosmic rays and solar wind, further eroding what little remains of its protective layer. Yet, this relentless stripping also offers a glimpse into the ancient processes that shaped our own solar system. revealing how planets evolve over billions of years. Particles from space bombard Mars incessantly, each impact contributing to the ongoing sculpting of its surface. These micrometeorites not only shape the dust, but also carry with them a record of the solar system's history. As they collide with the Martian surface, they embed themselves in the soil, carrying isotopic signatures that trace their origins back to distant stars and nebulae. This process, while destructive on small scales, provides scientists with invaluable information about the formation and evolution of our cosmic neighborhood. The thin atmosphere on Mars allows for a clearer view of the cosmos than what is possible on Earth, free from much of the atmospheric interference that obscures celestial objects. Astronomers could leverage this advantage to study distant stars and galaxies in unprecedented detail. However, as solar radiation strips away more of the Martian atmosphere, even this benefit will diminish, leaving behind a world where the surface itself becomes increasingly exposed to the harshness of space. The red dust, once again, is not just a passive residue, but an active participant in the planet's ongoing transformation, each grain telling a story of cosmic violence and planetary decline. As solar wind stripping progresses, Mars will lose more of its remaining atmosphere, leading to even colder temperatures on the surface. With less carbon dioxide available for greenhouse warming, the average temperature could drop further below degrees Celsius. This cooling would exacerbate the challenges faced by any future human settlements or scientific equipment left on the planet's surface. Yet, this relentless process also serves as a reminder of the dynamic nature of planetary environments and the delicate balance that sustains life elsewhere in the universe. The thinning atmosphere will not only affect Mars' climate, but also its potential for sustaining liquid water. As carbon dioxide levels decrease, so too does the planet's ability to maintain any form of stable surface water. Any remaining ice caps would sublimate more rapidly under increased exposure to solar radiation and colder temperatures. This transformation underscores the interconnectedness. The red dust of Mars, sculpted by cosmic violence, settles quietly under an endless sky untouched by sound. As we come to the end of this journey through the stillness of space, I hope you find peace in its quiet depths. Thank you for joining us tonight on Cosmic Sedation. If you enjoyed the trip, don't forget to subscribe and like. Good night, and may your dreams be as vast and serene as the Martian night.